point P is a distance b equals 5.5 meters above the center of a uniformly charged ring of radius a equals 0.11 meters in the plane, in the xy plane, with carrying a charge of 2.5 microcoulombs. Calculate the electric field at the point P. Calculate the z component of the electric field at the point P. So this is my charged ring, right? And it's producing electric field up here at this point P, and we want to evaluate what that is. You can probably see that it's circularly symmetric about the z-axis, and so, for example, if I take a little dq element here, it's producing an electric field in this direction. We can call that maybe E1 or something like that, or DE1. And then a piece on the opposite side over here is producing an electric field in the opposite direction. We can call that maybe DE2, it doesn't matter. And so these two guys will have components that, x components, or components in the xy plane that cancel, right? 2 points on the opposite side. And you can do that all the way around, so the horizontal components will cancel and the vertical components will add, right? And so if I just calculate one of these dE's to say this dq, I can say dE is equal to k dq over r squared, right? We know it's going to be pointing up the z-axis, so we could put a little k hat on that if we want to. And so we can ask the question, well, what is r squared? Well, r is the distance between here and here, so it's that guy, right? And so r is equal to just the square root of a squared plus b squared. And so the component of the electric field is just due to one little charge element is k times dq over a squared plus b squared, because it's r squared times k hat. And so if we want to, we can call that c, and we can say it's equal to k dq over c squared, or something like that, right? And so that's the element of an electric field that way. If I want to know the z component, dEz, right, that's equal to k dq over c squared times the cosine of this angle, which is the same thing as the cosine of this angle. We can call that theta if we want. I'll just erase that a little bit and call that theta, right? And so it's cosine of theta, and cosine of theta is this length over the hypotenuse. It's b over c, and so it's k dq times b over c cubed. Or if you want to go back to the way we had it originally, you could say k dq times b over a squared plus b squared to the 3/2. And so now somehow we have to integrate this around the circle, right? And so I can say really dq is just equal to the charge per unit length, lambda times dl, where dl is the length of the little section of the circle that I've taken my dq out of, right? And lambda is equal to q over the circumference of the circle. It's the linear charge density. It's q over 2 pi times a. Right? And so my dEz now is equal to k times my dq, which is lambda dl times b over a squared plus b squared to the 3/2. And now I can say, well, okay, I want to get Ez. That's just the integral around the circle, I'll just call it like that, of dEz, right, which is equal to the integral um, uh, which is equal to the integral of this quantity, k lambda dl b over a squared plus b squared to the 3/2 around that circle. But notice as you go around that circle, a doesn't change, b doesn't change, k doesn't change, lambda doesn't change, b doesn't change. dl just integrates around the circumference of a circle, and so I'll have to come up here and erase a little bit. And so what I can say is Ez is equal to k lambda b over a squared plus b squared to the 3/2 times the integral of dl around the circle, which is just k lambda b. I need to make a little more room here. Over a squared plus b squared to the 3/2 times 2 pi a. That's what you get when you integrate dl around the circle. You just get the length around the circle. And so this becomes 2 pi k lambda ab over a squared plus b squared to the 3/2. Remember, k is equal to 1 over 4 pi epsilon naught, and so if I want to write this in terms of epsilon naught, I can say it's equal to lambda ab over 2 epsilon naught a squared plus b squared to the 3/2, and that's my E sub z. Or I could say, I could also go from here and say Q is equal to 2 pi A times lambda, right? Because that's the circumference and that's the charge per unit length. And so if you go back to where I defined this thing, I said lambda is equal to Q over 2 pi A. And so I can say 2 pi A lambda and replace that with Q, and I get this is equal to k b q over a squared plus b squared to the 3/2. And so then you can substitute in the numbers and see what you get for Ez. So in this problem, we have a thin plastic ring of radius r equals 0.31 meters. It has a linear charge density of plus lambda, so plus lambda on this side. And we'll say it has a linear charge density of minus lambda on the other side. And it's saying, what is the electric field at the center of the ring, right? And so what I've done here is I've just drawn a little piece of the center. I'm just looking at, I have a little dq here, and it's equal to lambda times dl, or something like that, where the width of this is dl, and it creates an electric field at this point that's given by dE equals k dq over r squared, or k lambda dl over r squared. And since this is the positive half, it points away from this element in this direction. But there's an element on the opposite side, which actually ends up giving you the same electric field at that point. I can just say dE equals k dq, where it's this dq, right, over r squared is equal to k lambda dl over r squared. And this one's got a negative charge, linear charge density, but all I have to worry about is that the fact that that negative charge density is actually making it point in the same direction as this guy is, and has the same magnitude. And so I can say, the sum, if I want to say dE total for the two opposite points, for the opposite DLs, is just twice either one of those. It's 2k lambda DL over r squared. Well, you can kind of see that as we go around the circle, if we work them in pairs, right, the electric field's just going to go from pointing this way all the way to pointing that way. And so when you take into account all of the effects, the only ones that are going to matter are the ones that are the components pointing in this direction, right? And so if I start with this side and go up to here, I can just be taking the x components of these things. So in this case, it would be, so for example, let me just draw my circle here. Here's my circle. I'll just look at it as a complete circle there, right? And so now I'm looking at the electric field that's pointing this way. Say as I'm working around, it's due to these guys. If this angle is theta, right, then what I want is the vertical component of that. The colors no longer mean the same thing they did a minute ago where I was trying to do positive and negative. But I just want this component because this guy over here is going to have the opposite component to this piece, and they're going to cancel. And so the only ones that matter are going to be these two guys, and they're going to add up. And so the electric field is going to be pointing in this direction, and it's going to be the magnitude of the sum of all these guys as I go around the circle and just take their x components, their components along this axis. Furthermore, I can just go from here to here and double it, because the x component, the component in this direction on this side, is going to be the same. And so I can say to get E total, is twice the integral for from say theta equals 0 to theta equals pi over 2. In other words, from here to here of dE tot. And so I have to figure out what that does. That's so that's basically, you'll forgive me the limits for a second. I want twice the integral from theta equals 0 to pi over 2. And I'm just going to put this in there as this, well, this guy in here, right? 2k lambda dl over r squared. When I'm integrating all this theta, and so I have to be careful how I do this. This is my little piece dl. And so if you think of, if I want to do an integral over theta, this piece here would represent my d theta, right? D theta. And dl is equal to r, which is the radius of my circle, times d theta, right? That's how you get this piece here. It's just r d theta. And so this integral becomes 2 times the integral from 0 to pi over 2 of 2k lambda r d theta over r squared, right? And that'll get me the component due to this guy. But now I've got to get the sine theta, because I just want the vertical component of this. That guy is just a total electric field just due to the little dq elements on opposite sides. But I've got to multiply it by sine theta to get this piece of it. And so this becomes, after I pull everything out, I get 4k lambda over r, right? Because one of these r's cancels with that one. And then I get the integral from 0 to pi over 2 of sine theta d theta. And so the derivative of sine is cosine. Sorry, the integral of sine is cosine, or negative cosine. And so this is 4k lambda over r times the evaluation from 0 to pi over 2 of minus cosine theta. And so I have to come up to the top to evaluate that. And I get my total electric field is equal to 4k lambda over r times cosine of pi over 2 is 0 minus cosine of 0, which is 1, which is minus 1. Sorry, minus cosine minus negative cosine. So it looks like this. 0 minus negative cosine of 0, which is just 1, so it's plus 1, so it's 4k lambda over r. Or if I wanted to write it in terms of epsilon naughts, I would say it was lambda over pi epsilon naught r. And so then I can plug in and evaluate. So in this problem, we want to determine the electric field at distance z above a disk radius r with uniform charge density and charge q, right? And so the black circle is my main disk, and it's got a radius of r. I'll just draw it over here. Maybe that's my r, right? It's carrying total charge q, and so I can say its charge density is equal to q over pi r squared, right? That's the charge density. I want to know what the electric field is up here due to the whole circle, due to the whole disk, right? A distance z above. So this z never changes. That's my point P up there, say. And I want to know what the electric field is. So what you see here is kind of a drawing of a single ring of thickness dr prime and radius r. That's creating an electric field out here, and we're going to kind of integrate outward from the center with rings going from r prime going from 0 to big R, and essentially adding up the effects of all the little rings, because we've already done this calculation. So the expression for the electric field due to a surface is, at some point P we already talked about, is K, or 1 over 4 pi epsilon naught, take your pick, times the integral over the surface of the charge sigma dA, right? I have to integrate over the whole area over r squared times r hat, right? In this case, you can kind of tell by the symmetry of the problem that the electric field is going to point straight up. We've kind of already talked about that, because each ring is symmetric in the horizontal direction, and so the components that are pointing outward will cancel, and the ones that are pointing up will add up. And so this is just the general expression, but in our case, we're going to be taking for each angle theta here, as we integrate outward, we're going to be taking the cosine of that, and so we could say our integral is going to look like this. So P equals 1 over 4 pi epsilon naught. Again, the integration over the surface, right? Sigma times dA. However, we're integrating the surface over r squared, now times cosine of theta, times k hat, where theta is going to vary as we integrate from the center outward, right? So our MO for this, our solution, is going to be to use these rings. And so we need to sort of figure out what this dA is, right? Our integration on the surface, dA is going to be the area of one of those rings. And so dA is 2 pi r prime. That's the radius of this, that's the circumference of this circle, times dr prime. That's the thickness. And so the area of this ring is 2 pi r prime, its radius, times its circumference, its circumference times its thickness. And that's the area of that ribbon, that blue ribbon that's going around. And then if I multiply that by my charge density, this thing is my dq, right? So I'm integrating over to get my electric field. And so that's my dA. The r squared in here is this distance. And so the thing that's called r squared is really equal to r prime squared plus z squared, right? This is my r. this is the, in my electric field, it's the distance between the charge that I'm after and the point of the electric field, but that's just the square root of this distance squared plus that distance squared. And so in my problem, I'm going to do this. I'm going to write it this way. And finally, cosine theta is just this distance over that distance, right? Sorry, it's this distance. It's the cosine. It's adjacent over hypotenuse, so it's z over the square root of r prime squared plus z squared. And so if I make all these substitutions, my electric field at the point P becomes 1 over 4 pi epsilon naught times the integral. And now I can integrate this thing from 0 to r, because that's where my rings go, from a radius of 0 to a radius of the whole sphere, or the whole disk, right? And I just replace all these things. The sigma stays the same. The dA is 2 pi r prime dr prime. The over r squared is r prime squared plus z squared. The cosine theta is z over the square root of r prime squared plus z squared. And finally, I'm just left with a k hat. So let me just make sure I've got all my terms in there. Z. And so this becomes 1 over 4 pi epsilon naught times the integral of sigma times 2 pi r prime dr prime times z over r prime squared plus z squared to the 3 halves times k hat, if I want to write it that way. And so the z's are constant, and so I can pull all of that out, and I'm really just left with 2 pi sigma z over 4 pi, okay, I've got something, a thread or something on here, epsilon naught times the integral of r prime dr prime over r prime squared plus z squared to the 3 halves. And this is a lookup integral, and so I'm just going to look that one up. And write it at the top. But this isn't too bad, right? Because it's just, if this is a u, that's a du, right? The r prime squared, this is a constant. The z squared is a constant. The r prime squared, I could just call that u, and then du would be 2 r prime dr prime. And so you can see this is a pretty simple expression to integrate. And what I get when I integrate this is E of P is equal to 2 pi sigma z over 4 pi epsilon naught times what it integrates to is 1 over z minus 1 over the square root of r squared plus z squared times k hat, if you want to do that. And so so I can say this is equal to sigma over 2 epsilon naught. I can cancel the z's and I get times 1 minus z over r squared plus z squared, square rooted, right, times k hat. So there are a couple of things you can say. Suppose R is much, much greater than Z, right? And that's the case where you have like an infinite plane. And so you're really close to it, and as far as you're concerned, it's infinite in size. And in that case, this really, you can neglect this guy, and this just becomes Z over R, as R is much, much greater than Z. This term goes to 0, and you get the electric field at the point P is equal to sigma over 2 epsilon naught. And this is for an infinite plane. And that's a really important one, because a lot of times if you're just close enough to a surface, like if you were a centimeter off this whiteboard, this would almost look like an infinite plane. That'd be a really good approximation. So if you know the charge density on a surface, then you know the electric field near the surface. And so that's really useful. We can do the opposite. We can say, well, what happens as the electric field gets, as you get really, as Z is much, much greater than R, and it's a little harder to see. So I'll do that here in a second.